35 on Zoom. Howdy. So do we need to unmute? Oh, this is already unmuted. Thank you all for being here. We're very excited to have Dr. John Soro, who is the Deputy Director of Los Alamos National Lab for Science, Technology, and Engineering. So it's sort of, he manages pretty much everything at Los Alamos, everything that certainly we are very interested in. He's a physicist. He has a bachelor's degree in physics from Stanford, PhD from UCLA in condensed matter, experimental condensed matter physics. Then he was a postdoc at UC San Diego. Then he joined Los Alamos in 1997 and went up through the ranks. And now he manages one of the largest programs. He has a lot of awards, the most recent being the 2013 Lawrence Award for his work in superconductivity and new materials. We're very excited, and his theme of the talk is opportunities for physicists or nuclear physicists or engineers at Los Alamos, who is going to hire Los Alamos is going to hire a large number of people over the next few years. So certainly there are a lot of opportunities, not just research, but also the pipeline. As a token of appreciation, this is a laser pointer for you.
Cool.
Nothing is more advanced than anything you ever worked on. It's a green laser.
Excellent.
And I did put the battery and it does work.
I tend not to use pointers during talks. Maybe I'll have to, but it's just cool and it's green. So.
Yeah, and then that's your.
Great. So thank you, Rupak, for the introduction. I think my microphone is on, yes? Yes, all right. So as Rupak said, I'm delighted to be here. This is not going to be a talk about my personal science. Rather, I want to talk about sort of lab overview, because I think one of the things we find is places like Los Alamos, where I've sort of been my whole adult life. Of course, I know what it is. People hear Los Alamos and say Manhattan Project and off in the desert of New Mexico, and it kind of stops there. So I want to talk about sort of, I'll do a little bit of facts and figures because that's kind of necessary for talks like that, but really focus on what our mission is, the range of things we do, the range of opportunities, and talk about strategy, and certainly leave time at the end for discussion. But whether you're on Zoom or you're in the audience, don't be shy about asking questions. I would consider this talk to be a success if I actually run out of time before I run out of slides, because you asked more interesting questions than the thing I was saying. So don't be shy about chiming in. I'll do a less sort of eloquent version. Uh-oh. Do it this way, I guess. I'll do a less. I'll do a less eloquent introduction than Rupak did. Thank you for the nice introduction. More give you a sense of sort of my own path, mostly to highlight the diversity of things when good at a place like Los Alamos. So I would say I was like many of you. I was an undergrad. I really had no idea what a national lab was. Between my junior and senior year, I spent 2 weeks actually at Lawrence Livermore, which is another national laboratory. Went to Los Alamos for a summer in 1990, and I don't have time to tell the story, but the story was such, I was planning to just go there for the summer and then come back and keep going. But I kind of never went back, and I spent all of grad school at Los Alamos. So I actually don't know hardly any of my colleagues at UCLA because they were at UCLA and I was at Los Alamos. Bounced around as a postdoc and have been at Los Alamos now straight for, that's a really big number, I guess 25 years almost. And I would say my career has been divided between honest to goodness full-time research in condensed matter physics, a time when I was pretending to be a manager and pretending to be a scientist, and it's pretty clear now all I do is manager, which is fine, and I'm happy with that. But that's mostly a point of there's a variety of things we can do. As Rupak said, my technical expertise is in materials research, but I actually led computing for us for quite some time, and now have a large part of scope that I'll talk about as we go along. In a similar spirit, and so part of the challenge of Los Alamos is it is kind of big and kind of complex. And so when we talk to people from the government, one way we represent that complexity is in the map shown in the right. So the gray outline is the Los Alamos campus. The red box is the District of Columbia. And so especially on days like today when the government is trying to shut down or not, that complexity becomes important in that regard. I apologize, the Zoom box overlays some of these numbers. The things that I'll highlight are, one, our overall budget is $4 billion, and I'll give you a flavor of that. An interesting thing to note, and it's sort of covered up here, but the average age of us is 43 years old. So for this room, you would say that's really old people, and you're probably right. It's also the case that just a couple years ago, our average age was over 50. So it's coming down dramatically due to some of this hiring that Rupak alluded to. We'll talk about where those opportunities are. So we're actually basically a decade younger than we were 5 years ago because the demographics are changing so much. And I think the rest I'll talk about in other places because it's kind of hard to see here. So before I talk about Los Alamos in specific, it's worth noting that the Department of Energy has 17 different national laboratories. And this is actually a representation of all of the 17 labs and their logos that actually all the labs agree on. So it's actually kind of rare that they all agree on anything. But this rainbow framework they agree on. And the ones around the outside tend to be larger. They're scattered around the country. There actually aren't any national labs in Texas, I don't think for any particular reason. But the bigger ones are around the outside and the smaller, more focused ones are on the inside. And so depending on your particular discipline, you might know one or several of them, but I think few people know all 17. And certainly in discussion, happy to talk about what each of those do. The biggest of the labs are the three so-called multi-purpose national security labs. Ourselves, Lawrence Livermore in California, and Sandia, which is more engineering-centric than science-centric, which has a footprint both in New Mexico and in California. And we can talk about that as well. One of the things I'll talk about in this discussion is Los Alamos is an NNSA lab, a National Nuclear Security Administration laboratory. So part of our day job, which dates back to the Manhattan Project, is we're responsible for stewarding the US's nuclear deterrent. So we'll talk about what we do in that space. It's also important to note we do a whole bunch of very irrelevant science, really cool, exciting science that has nothing to do with the nuclear weapons program. And so some people you can work anywhere on that continuum you want, and I think that's part of what's exciting. Because of that, one other important feature, in addition to sort of this arc of all the laboratories, is the set of activities that are part of NNSA. And what's different about NNSA is we actually make products. So the nuclear weapons themselves, the physical objects, not just the science behind them, are actually manufactured by NNSA. And relatively close to here in Amarillo, the Pantex plant is where they sort of all come together. So a feature of Los Alamos that I'll talk about is we're both a national laboratory, and I'll describe what that means in a second, but we're also a production complex. So we go from doing the most fundamental basic physics to actually making parts. And that's actually changing over time, and it's a big part of why we're growing. And there's a different set of other institutions involved, both in the design side and the production side. And we can talk about that if folks are interested as well. So let's get to Los Alamos in specific. So I told you our budget is $4 billion. Just 3 years ago, it was $2.8 billion. So we're more than $1 billion bigger than we were 3 years ago. That's a big number. That's bigger than all but 3 of the national laboratories. So we have grown more in 3 years than the total size of 14 of their laboratories. That's a pretty daunting thing. If you look at our budget in the royal blue, somewhere between 2/3 and 3/4, depending on how you count, is associated with the nuclear weapons program that I'll talk about in some depth. But a solid third are a whole bunch of other things as well. And I'll try to give you a sense, not in a budget pie chart, but in sort of a mission and strategy perspective, how those things are connected and what those opportunities are. As I said, we're growing rapidly. So the blue bars are how many people we've hired in each of the last however many years. So we have hired more than 1,000 people now for 6 years running. And so when you try to hire that many people, it's frankly exhausting because you're trying to find high quality people to come work for us, and that's a hard problem. Part of why those numbers are so big is, yes, we're $1 billion bigger than we were 3 years ago, but also goes to the average age thing. So the golden bars are the number of people who have left. The vast, vast majority of them are people who are retired. So when you're a relatively older laboratory, when you've got a lot of 50-somethings and 60-somethings, and they're fading away, and your budget is going up, the population goes up pretty dramatically. And so part of the theme of this talk is, yes, we would love to have you come work for us. This is not just the jobs talk. This is also a collaboration talk, because a lot of the stuff we're interested in doing, all of you here are doing as well. So if this talk is successful, some of you might be interested in coming to spend, just one summer and staying for the next 30 years, or doing something different, but also doing collaborations together. We'd love to have some of you come work with us while you earn your degree here as an undergrad or a graduate student or whatever. That's part of the opportunity space. One important point to mention here, and I'll mention it in several places, because it's a misconception about Los Alamos. Some people hear Los Alamos Nuclear Weapons Lab, and they therefore infer, therefore US citizens only. That is decidedly not true. So any particular day at Los Alamos, there are more than 500 of us who are not US citizens. And that's a totally good, totally positive, perfectly reasonable thing. The demographics of our postdocs, for example, look just like any other large research university. The average large research university is at least plurality non-US citizens. That's totally fine, that's good. We need the smartest people around the world. And that's true of the laboratory as well. So don't make the assumption, Los Alamos, national security, no foreign nationals. That's a flawed assumption. So our budget is big. We need lots of people because we're growing, and some of us are old like me. There's a big time hiring opportunity. That means that our student programs and our postdoc programs are really important. So two of the factoids you couldn't see in the earlier slide, we have about 500 postdocs at any moment in time. And so that's the biggest of any of the laboratories. So that's just a lot of postdocs. So we're not a degree granting institution. So you don't come to us to get your degree, but you do come to us to do research. And in a lot of disciplines like physics, a postdoc is a natural part of that path. Of those 500-ish postdocs, about a third to 40% of them get converted to staff. So they come as a postdoc, they spend their 3 years, we like them, they like us, they become permanent staff, and they stay forever. In the other direction, if you go to an auditorium like this of us, and you say, raise your hand if you came to the laboratory as a student or a postdoc, depending on which particular slice you take, it's more than 2/3. So our student and postdoc programs are a ginormous source of talent for the laboratory. One measure of that is shown at the top and the top right. So the blue line is the postdoc count. I guess as an orangish color. We were running about 1,800 students a summer, people coming from College Station, moving to Los Alamos for 10 weeks, up and through 2019. Obviously, in the summer of 2020, that would have been reckless to say, let's move 2,000 students into a small town like Los Alamos in the middle of a pandemic. It would have been a disaster. So we actually worked really hard and virtualized our student program. And so we actually had 1,100-ish students. The vast majority of us both of them work from home. They didn't actually come onto our physical campus. The exciting number that's actually blocked here is that this last summer, just a few months ago, it was actually up to 1,650 again. So it was almost as big as it was. And of those 1,650, half were in Los Alamos and half were scattered around the whole rest of the planet. So if we've been successful through the pandemic, we're gonna have student programs as big as ever. So half the people being here and half being someplace else, and that's a win. That's all I'll say about that. All right, I'm almost done with facts and figures. So where do physicists live at Los Alamos? In org chart space, they live everywhere. So again, reasonable misperception. We have an organization called the Directorate for Physical Sciences. And in that directorate, there's a division called Physics Division. Physics Division has actually existed since 1943, since the Manhattan Project. Essentially, everyone in Physics Division is a physicist, no surprise. But there are lots of physicists scattered everywhere else. Obviously, there are physicists who do simulation and computation, probably including some of yours. Some of our physicists come from physical science areas and work directly in the weapons program. I'll give you a flavor of that work. A variety of them work in our global security program. And so I think that's one of the opportunities. If you want to come to Los Alamos and stay in physics division your whole life and do work that's a lot like what faculty here do, that's a perfectly great career path. But there's also tons of places around the whole rest of the laboratory where physicists live. I'll try to give you a flavor of that. One other thing, so I should say just for completeness, I guess, oops, wrong direction. For completeness, as Rupak said, yeah, there I am. So the lab has 3 deputy directors. I'm one of 3. All of the sort of ST&E base works for me. So all those people are the 4,000 people who work for me. In addition, though, and I'd say more importantly, all of the things that the laboratory does to enrich our research base is part of my organization. So the student program that manages all 1,600 of those students works for me. The office that runs all the postdocs works for me. But I'd say most importantly for this conversation, there's an office called the Office of Partnerships and Pipeline, which does everything we do in partnerships and pipeline. And it's a relatively new office, and it's been pretty successful in bringing a whole bunch of stuff together. There is a direct connectivity to the Texas A&M University National Laboratories office. So Diane Hurtado here, who runs that office, talks to Nan Sauer like 3 times a day, every day. So I'll show you some people who you can talk to make connections at the end of the talk. But a great route to make that tie is from this office directly to us. All right, so enough facts and figures. Let's talk about the mission of Los Alamos and sort of what our job is and what we're trying to accomplish. So if you start in the upper left, I already said that our principal responsibility is to ensure the safety, security, and reliability of the US nuclear stockpile. The one thing that our director has to do every year, and he actually is doing it probably literally today, is he has to write a letter to the president that says the stockpile is safe, secure, and reliable, or it's not. And that's a feature of when the United States stopped doing nuclear testing back in 1992. How would you know they're actually going to work if you wanted to use one of them? We do science to say, yes, it's all good. And that's the one thing my boss has to do every single year. Lots of people know that we do physics and design of weapons. But if I'll give you a flavor, we also do a whole bunch of engineering and production. So we'll talk more about that in the next set of slides. As important as the weapons program is, it's actually only a small part of the national security enterprise. So if you look at the triangle in the middle, the nuclear deterrent is one piece of national security. But we also do a ton of work in non-proliferation, working with our peers, our friends, our allies, to make sure that we can use nuclear things for like energy, for example, in a positive way. And there's also counter-proliferation, because not everyone is like-minded, and so you want to make sure that people aren't doing reckless and dangerous things. In addition to all that nuclear stuff, though, there's a whole bunch of other national security challenges. We're kind of living through one now in sort of the pandemic, because the pandemic is a public health problem, but it could also be a biothreat problem. We're experiencing lots in cyber in that space. So there's a lot of work we do in the bottom 2 parts of the triangle, which we call global security, and I'll give you a flavor of that. And then, yes, we do a lot in energy security, just like all of you do, and a lot of very fundamental science. So when I think about this slide, one of the things that's important to me is that all the arrows are 2-headed. The work that we're doing over here feeds back all the way to the weapons program. The reason we're really good in certain parts of very academic, very fundamental physics derives from the weapons program work. So I view it as sort of 2-headed arrows across the slide. That's hopefully interesting to you, but I would also say, as an individual, you can live anywhere across this continuum. There are roles to play at Los Alamos in any of those spaces, whether what you want to do is completely work on the stockpile or not at all work on the stockpile. There's tons of opportunity in that space. So I'll try to sort of walk through this triangle in more detail over the next handful of slides. So I already alluded to this. It used to be the case that the way we figured out whether our nuclear weapons actually worked was we took them underground in Nevada, we pressed the button, and if the ground shook, it was a really good day. And you got these so-called subsidence craters out in the desert in Nevada. And if the ground didn't shake, it was a pretty sobering moment for the designer who thought it was going to shake. And there certainly were days where it didn't shake and more days that it did. We, the United States, have not done that since 1992. I would say that's a really good thing, because setting off nuclear weapons in the desert is probably not the most effective way to solve the problem. So what we've had to figure out is, how do we do science to have confidence that if we were going to use one of the weapons, it would actually work without actually testing it. And since it was 1992 when we stopped, it's been more than 30 years. So the question is, how do you over 30 years still have confidence something's going to work if you were to choose to use it? That's built on a whole bunch of science, and I'll give you a flavor of that science the rest of the talk, a big piece of computing, a big piece of materials, and a big piece of physics. And today, we actually believe we understand how weapons perform better than we understood 30 years ago, even though we haven't tested them, and all of them are 30 years older than they used to be. So that's a very big triumph of physics and science. In addition to that sort of physics piece of it, there's also a very large engineering piece, and there's a very strong partnership between our physicists and our engineers. So it turns out that in the previous slide, I think it said there are 7 different systems that the US has in our nuclear stockpile. They go by numbers like W whatever and B whatever. The approach we've been taking over the last decade or so for these systems that are now 30 years old is we do what are life extension programs. We frankly spend a lot of money and a long time to refresh them, to sort of take care of their parts that are aging and make them fresh. There's a ton of work to do in that space because many of the ways we built these systems, you can't build anymore. So you have to figure out how do you make materials that have the same performance characteristics, not using the same processes, for example. One of the interesting things we're doing, just starting quite recently, is there's a system to build a replacement for one of these that we're starting from scratch. And so it's not going to actually change the overall performance, but we're going to make them differently. And so there's big opportunity in that space. And then finally, the biggest piece of why we're growing is our production responsibility. As I said, we actually make physical objects that go get handed off to the Air Force or the Navy. That's part of what we do. We've always done some of that, but the piece that we're working on now is there's a component of a weapon called a pit. It's the plutonium object at the middle that drives the first fission reaction. The United States has not had the ability to make pits in quite a number of years. And we're now tasked to make 30 of those a year in a reliable way. It turns out once you forget how to do something, it's actually pretty hard to relearn it. And doing that at scale is pretty expensive. And so that's driving our growth. An important part of that, and this is actually an example of my own personal research, this is not at all a plutonium pit. It has nothing to do with a nuclear weapon. It's a single crystal of a plutonium superconductor that I happen to grow. So if you like the weapons mission, that's great, tons of opportunity. If you just want to do perfectly interesting, perfectly academic actinide science that you publish in Science or Nature, big opportunity there as well. And so, I think the takeaway of spending some time talking through what we do with the nuclear weapons program is for some people, that's a very attractive thing, an important opportunity to contribute to national security. If that's what you want to do, we would love to have you. If that's not your cup of tea, that's totally fine too. There's other broader things to do. I think that's the opportunity of a place as big and broad as Los Alamos. So now let's pivot from that upper left on that triangle slide to the middle. So I'm going to talk a little bit about what we do in global security, those 2 bottom parts of that triangle, and what we do in very open and very fundamental science and energy. And so the code is the yellow part's the part I'm going to talk about first. So I told you that we work on non-proliferation. We do a lot of that. And then the acronym soup of SPP OFA is work that we do for other parts of the government. So what the heck do we do in that space? So there's sort of 2 catchphrases that I'll use to describe it. One is a quote that I'll attribute to one of my colleagues, and she says, it takes a weapons lab to find a weapons lab. So if you're trying to figure out whether the other country is doing something they shouldn't be doing, a simple way to do that is to say, do they look like us? Because if they look like us, they're probably doing similar stuff like us. And if they're partners and they're open and transparent, that's all good. But if they're saying, no, we don't do that, but it looks like they do, that's a challenge we have to go work. And so a big piece of that is us doing that work. And part of the point of the middle part of the slide is all the work we do for the weapons program lets us do that well. So we design our own weapons. That means we're actually pretty good at reverse engineering other people's systems. We can say, are they doing the same things? Do they have the same design principles? And our systems are relatively old. So it's frankly not that exciting to go redesign something that's 30 years old. other countries are actively building new nuclear weapons every single day. Figuring out what they're doing is a pretty stimulating thing. And one of the sobering realities is if we have some information on another country's approach and we ask our most senior, oldest designers, would this work? They say, nah, it wouldn't work. It doesn't look like ours at all. We take our really smart new hires and say, can you make this thing go? And the answer is yes. Now, it's not as sophisticated and safe and reliable as our own stuff, but it still works. And so, you know, there's clearly a built-in, we're set in our ways, and so we need new technical challenges in that regard. Same thing in terms of, you know, we have to surveil our own work. That means we're good at nuclear counterterrorism. That means we have actually a very large footprint in space. We, Los Alamos, have had satellites in space trying to detect nuclear detections for more than 50 years. Again, if that's your thing, that's awesome. If all you want to do is really cool space science, the Mars Rover shown on the far left is also a big part of us. We are the ones who made the nuclear heat source that powers the rover. And 2 of the instruments on that rover are actually built by us, including the first microphone that's ever been used off planet. So we actually have a microphone listening on Mars to what it sounds like when the Martian wind blows. It's kind of cool. I probably should have put the tape in the slides, but I was too late. Similarly, we've got lots of expertise in materials of various sorts. I already gave an example of my own work on sort of plutonium superconductors. But again, you know, that kind of expertise for national security reasons directly informs work we're doing on COVID. So we've been very active in the science of COVID and doing epidemiological modeling based on that understanding. And so that goes to the other tagline, that we are a test bed, and one of the things we do is experimentally evaluated intelligence. So what'll happen is our government partners, the CIA, the DoD, will say, we found this thing, it looks like it might do this in whatever space it is. You know, is that possible? Well, we go try and make it work. And if we can make it work, somebody else probably can. And if we can't figure out what it's for, there's a chance that it's nothing. So those 2 things drive the rest of the triangle. So now let's move further to the right in that original slide. And so now again, code is what we're talking about. So yes, we have a large national security footprint. It is very important to the security of the nation. But we also have a very broad open science effort. So I'm going to spend a few slides talking about the open science we do that has nothing to do directly with the nuclear weapons program, but is informed by that. That includes a large body of work for the Office of Science. Some of the faculty here also do work for Office of Science. We're working with the same people. And a lot of work both in applied energy of various flavors and also nuclear energy, and I'll describe that for you in some detail. So I guess a point to make in all this space is it can be as dual use or as not dual use as you want it to be. So it turns out that the Department of Energy has a consensus climate model called E3SM. We, Los Alamos, are key players in that space. We are the world's expert in modeling sea ice and how when that ice, especially in the Arctic, melts, how it affects ocean temperatures. It actually started a really long time ago when people were trying to understand what would happen in a nuclear winter kind of event. So there's an inspiration in the nuclear stockpile, but now it's just climate change and climate science. And so everything I'm describing here is very open, from very fundamental to very applied, and includes people in the upper right. That's an icebreaker. Back in 2020, they thought they were going on sort of a 60-day tour in the Arctic to sort of make climate measurements. Then the pandemic hit, so they got stuck being there for 9 months. So that's one of the consequences of the pandemic is the ability to fly people in and out kind of went away. So they spent a much longer time doing that. But the kind of work they informed, the kind of model stuff shown here. So entirely open, entirely trying to address questions like climate change. The opportunity we have, because we're a national security laboratory, is we can make all of that local and understand impacts. Whether that's impacts like coastal resilience and geoengineering and things changing, or it's defense applications like, you know, what if the Arctic melts and there's a new Northwest Passage, what does that apply? We can work on both sides of those things, including the sophisticated versions of today's nuclear winter and questions of regional stability. So there's the opportunity to work on both sides of the line, but no requirement. Similarly, and hopefully not surprising, we're very active in nuclear energy. So we work directly for DOE's Office of Nuclear Energy. There's another picture of the Mars Rover. We're kind of sort of, you know, fixated on the Mars Rover at the moment because that's going pretty well. We also work across a variety of agencies, again, trying to advance nuclear energy for the US. But even if the US doesn't have a clear policy in that space, there are lots of companies that want to try to build stuff. And there also are other countries doing the same thing. So it's an area we need to lead in, whether we actually have a forward-leaning nuclear energy policy as a country or not. And it seems to be gaining a whole lot of energy in that space. Obviously, lots of work for physicists here as well. We also work on the full gamut of clean energy, renewable energy. So we have the country's largest fuel cell program. So we built the first fuel cell vehicle back in the 70s and have a very large program. You would ask, why is Los Alamos any good at fuel cells? Well, we had some smart people at the time, but it turns out some of the same extreme corrosive environments that make up fuel cells are actually applicable to nuclear weapons. So our clean energy people are helping our stockpile people work hand in hand in that space. It's also the case, though, that we're not that unique in that space. You know, all of you could make an argument we're just as good as Los Alamos in that. One measure of our success for us is we're involved in a whole bunch of consortia. So the point of the acronym SOUP here is each of these are large multi-university, multi-lab collaborations, whether it's trying to understand the impact of plastics on the environment, whether it's the current frontier of fuel cells, which is trying to make a large truck that can go 1 million miles, whether it's working on grid stability, including in partnership with Texas A&M. When we succeed in this space in these large consortia, that's both a validation that we're good because other people are asking us to partner, and it says we don't have to do everything ourselves. And then finally, to get to the most fundamental stuff we do, it's the work that we do for the Office of Science. And again, many faculty here work for the Office of Science as well. From a physicist perspective, basic energy sciences is the place where all condensed matter physicists get funding. There are big pieces of fusion, and then especially high energy physics and nuclear physics here where Texas A&M is quite strong, as well as computing. So it kind of runs the gamut from very centric, very deployable nuclear weapons research all the way to the most frontier stuff we do. And so from my perspective, again, it's a question of, are the arrows all two-headed? Is the stuff we're doing here helping inform our core mission? But I think from a career perspective, it means you can live anywhere across the continuum. So I'm going to change gears a little bit because that was sort of the walkthrough mission. And I want to talk a little bit about strategy and some things that we call capability pillars. So what's our top line lab strategy? It's a phrase that we call simultaneous excellence. And what simultaneous excellence means is all we have to do is do 4 things well. We just have to do them all at the same time. So I've already talked a lot about the first 2, because the first 2 are, we've got to be excellent in nuclear security and we have to be excellent in science, technology, engineering. And so part of that is how do, on the one hand, you actually deliver components on very real schedules against active threats? And how do you do the most frontier science possible that's all discovery science, anticipated unknown unknowns? And there should be constructive tension there. And the whole last part of the talk mostly talked about that, so I'll skip that. The other 2 things that are important here are we need to be excellent in mission operations. And I would say from a laboratory perspective, we know that because when we don't do it well, when we make safety mistakes, when we make security mistakes, we get in trouble. And when you get in trouble, you can't do the fun stuff you like to do. That's true. That's a fairly reactive view of being excellent in mission operations. The thing we're trying to do as a laboratory, and it's part of the culture that I perceive here at Texas A&M, is when you do that well, you can do really cool, really spooky, really dangerous stuff that nobody else can do. So part of our strategy is to make that go from reactive to proactive, because we can do stuff nobody else can do. And then the last thing is you have to be a good neighbor. You have to be a good neighbor because sometimes we'll make a mistake. And if you don't talk to your neighbors ever and you call them that we made a mistake, we're going to explain it to you, they're going to trust you about this far. But also a part of being a good neighbor is saying, we, Los Alamos, don't have a unique claim on any of the stuff we're doing. We need partnerships and collaboration. So talks like this are part of being a good neighbor. We need our international colleagues to help us. That's part of being a good neighbor. And so if we do those 4 things well, we're being simultaneously excellent. And so that's our top line strategy. And it's worth thinking about the last 2 on the bottom as a complement to the 2 on the top. In that spirit, one of the things we've done in the last couple of years is actually adopted a lab culture statement. So our culture statement is how we do our work is as important as what we do. That means that the bottom two circles are as important as the top two circles. It also means that, yes, we actually have to think about safety in a proactive way. And so I won't read them to you, but if you look at these 8 numbered things, these are attributes of our safety culture that we aspire to. That's part of making this pivot from being reactive to proactive. It also means we have to treat our people well. So the less eloquent version of how we do our work is as important as what we do is I'm not interested in heroic jerks. So do we have people who do heroic stuff every day? Yes, absolutely. Is that an excuse for breaking safety and security rules? No. Is it an excuse for treating their colleagues poorly? No. So you can't be heroic. Well, you can be heroic and a jerk at the same time. I just don't want you working for us if that's the case. And so it's very much part of how we think about diversity, inclusion, and belonging. Because I think for many organizations, just like many organizations, our demographics aren't as good as they should be. If you only focus though on demographics, you're never going to succeed. If you try to create an environment where everybody feels welcome and feels like they belong, the numbers will almost take care of themselves. And so the safety idea and the notion of inclusivity go very much hand in hand. One place that comes home to roost is how we think about students. So I told you we have tons of students. I told you we got tons of you to come work for us. I have a different conversation with our managers and mentors of students. Because what we need to commit to every student who comes to us is that the managers will actually know how many students they have and do right by them by talking to them with some frequency and giving an opportunity to highlight their work. And I've had managers say, well, I have too many students. I can't possibly know what they're all doing and give them a chance to highlight their work. And I will say, exactly, you have too many students. Because we owe it to our students to have a positive experience where they feel included and feel like they belong, so they come back in the future. And so, well, that's not sort of the mainline sort of what does a physicist do, it's an important part of what we're trying to accomplish. All right, so the next piece of simultaneous excellence is what are those specific S&T topics that we're focused on. So I won't talk about any of these in particular, except to highlight a couple that haven't come up yet. Because one of the questions becomes, and I'll talk at the end about how we invest our own discretionary resource. We invest it topically in these areas. And if you ask, what's the opportunity for physicists? 2 that I've not yet talked about are the 2 bolded here. So we have a very deep interest in accelerators, both for accelerator science and for using accelerators for materials and physics research, just like you guys do. There's a key opportunity there. And again, just like you guys do, we're very interested in the nation's quantum initiative, and we're working to grow that scope across the full range of physics. So we could talk a lot more about that, but I think I'll leave that for questions. Instead, what I want to spend a few minutes on is how do we think about the longest term science, technology, engineering we do. And so we don't actually have departments like all of you have. There's a physics department and the chemistry department. There are organizations that look like that. But because we're very focused on interdisciplinary research and teaming, we have what are called capability pillars. And it turns out that there are 6 capability pillars. These are areas of science, technology, engineering in which we think we have to lead. And if we're succeeding, people from a variety of departments come together to work in our materials for the future area. Whether they're condensed matter physicists, whether they're solid state chemists, whether they're material scientists, they all come together in that community. Same across all the rest. And so what I'm going to do is quickly click through a slide for each of these 6 to give you a flavor of what our priorities are and the kinds of research areas we're thinking about, very much through the lens, the bias of the physicist. So if we start with materials, because that's closest to home for me, one of the things we think about, and I'll just jump to the bottom, is there are 7 areas of leadership. So when we think about the whole range of materials research, what are those areas in which we have to lead? We think it's those 7 areas, from things like actinides and core electrons, which are very close to my heart, to things like nanomaterials, to things like complex functional materials. Those full range of areas are sort of deeply important to us, and we think we have differentiated strength. So if those areas line up with your interests, I think there's an opportunity there. maybe of greatest interest to this audience is the area that we call nuclear and particle futures. And so what we do in that space is we bring together the very most fundamental stuff we do in nuclear physics, particle physics, astrophysics, and cosmology. And we couple that with our people who work in applied nuclear science and engineering. So it is quite common that somebody comes to Los Alamos to be a postdoc working on a big particle physics experiment, developing detectors. They're really quite good at that. Some people do that their whole lives. Others will say, I figured out how to build big detectors and measure very rare events. I'm going to apply that to nuclear weapons experiments. And so the most sophisticated experiments we do uses that same skill set. People move back and forth across this. We're also very interested in high energy science, sort of what happens when solids stop becoming solids and become plasmas. And I already said accelerators are both a frontier of themselves and a key enabler. So a very large part of our physics community works in this space. And in all these slides, you'll see cover art of what our strategies are. And we're happy to share the specific strategies in those areas of what we're trying to accomplish. Again, both from a jobs perspective, but also from a collaboration perspective. The third in this space is information science and technology. And what I would say here is, of course, compilation and simulation and data science are important. One of the things that we think is the fact that we bring physics-informed knowledge is differentiated. So in the space of artificial intelligence and machine learning, lots of people do pattern recognition. That's not particularly unique to us. But where you can bring the underlying physics knowledge, you can make a difference. That's where physicists like all of us, partner with our computational colleagues, can really make a big difference. So I'll go more quickly through the last three, which focus on the science of signatures. This is an area where it goes very much back to sort of the work we do in global security, where it's on the one hand, how do I discover some signature of something I'm trying to understand? And how do I build a way to measure that? And that's, I think, what physicists often do. I think part of the challenge here is saying, how do I take those exquisite measurements and translate them into very extreme environments? You know, it's one thing to build a Raman spectrometer and measure a sample in your desktop in your laboratory. It's something else to have a Raman spectrometer in Mars. And once you hit the launch button, you can never go back and touch it again. We have a Raman spectrometer taking Raman spectra every single day on Mars today. Equally well, if you're trying to measure in sort of counterproliferation space, what some country who by definition doesn't like us is trying to do, those are also pretty extreme measurements. And the same measurement methodologies we're using on Mars, we're using to surveil other countries we don't want to talk about. That's a big part of this space, including actually deploying it. One of the things I didn't talk about early in the talk, and so I'll touch on here, is the first four areas I described very much contribute to the weapons program. But in addition, there's sort of a systems thinking that's unique. And that's especially true because, as I alluded to, the stockpile is evolving. It's going from a very old, very Cold War, how do we send very large nuclear weapons at our sort of single adversary, the former Soviet Union, how they send them to us. That landscape is very different. So the considerations that go into how you design in that space are very different. And so we're trying to think about that space and understand questions of integration, questions of how you do production and manufacturing in modern ways, and also systems analysis. And so it builds on all the rest, but it's different because there's something unique about that systems thinking. That same way of thinking is exactly the same as how we think about complex natural imaging systems. So if we're thinking about problems like climate change, for example, yes, you have to have physics and chemistry and modeling, but they come together in a systems way to try to understand it that's different. And so both this one and the one before it, I would really think about the systems overlay. Sorry, got to stop clicking in the wrong place. That was really bad. So the point I was going to make was all four of the top four are very discipline specific ways to talk about. But in addition, both complex natural energy systems and weapon systems add a systems overlay that brings the whole thing together. The next layer in that is, and it's easy to say in a community of physicists, there are many engineers who say Los Alamos is a physics laboratory. I would say that's probably good, we're all physicists. We need engineers too. And so one of the debates we've had is, should engineering be like the seventh area? And what we've concluded is engineering is really central to everything because we're trying to translate things to practice. And so while we think about systems thinking differently, we purposely don't think about engineering in isolation because we need our engineering colleagues to work with us. And so we think about engineering as the consummate crosscut in that space. And at least our engineers seem to appreciate the opportunity to contribute to science and technology across the whole continuum. All right, so let me try to wrap up, and I want to say a few words about sort of people. So kind of move it back. There we go. So let's say a few words about people. So I've talked a lot about mission. I've talked a lot about strategy. You can ask the question, do you actually put your money where your mouth is? Because otherwise it's just so much talk from a manager doesn't actually help me. So the short answer is yes. One important way we put our money where our mouth is we have a thing called LDRD, Laboratory Directed Research and Development. And what we say is we are going to tax all the programs that give us money. We're going to tax them at the 6% level and scoop all that up so we can fund fundamental basic research that prepares for the future. When your budget's as big as our budget is, that turns out to be $180 million a year. So that's a pretty large chunk of money. And we spend it to accomplish three things. We spend it to accomplish mission agility. How do we take basic research discoveries and translate them to direct mission impacts? We spend it to advance technical vitality. How do we make really smart people even smarter, especially working in teams? And overtly, we spend it on workforce development. So as an example, it turns out of these 500 postdocs we have, there's a competition every quarter. The top 10% are called directors funded. That means they're free to the individual PI. Our very best postdocs, we just cover off the top. We've also created an early career program that says, yes, all of our physicists, all of our scientists are smart. We're going to create a particular competition just for those people who've been here for less than 3 years, to give them the chance to go do their own thing and sort of make their own discoveries, not cut up in bigger teams. And so that focus on mission agility, technical vitality, and workforce development, which we spend across a whole bunch of slides, which I would love to give an hour talk on, but that would not be very interesting to this audience, shows that we're putting our money where our mouth is. The other way we're putting our money where our mouth is this box that I described in terms of partnerships and pipelines. So I've already made the point that we have very large, the largest student program of all the DOE labs, and either the first or the second largest postdoc of all labs. We have that. We have a variety of outreach efforts that engage both with entities like Texas A&M, like New Mexico universities, like Tech Transfer we do. And the thing that we did was stick them all in one place so it all works synergistically. And we're being much better partners as a result. In addition, the point that I'll highlight here is this piece called the National Security Education Center. So what that has is 6 different centers, and you can read the titles, I won't read them to you. But again, those are areas of importance to us where we've created specific organizations to focus on outreach and pipeline and student and collaborative engagement. If you read the titles, or at least where the titles are opaque, read the bullets beneath them, that's hopefully directly identical to the things I talked about. So it's an example of we're saying our priorities are what our priorities are. I do know how to count. It's not 6, it's 7. So what's the 7th one? The 7th one is the Joint Center for Resilient National Security. That's actually an explicit partnership between Los Alamos and Texas A&M, where it's partly doing the science of this weapon systems pillar I talked about, this sort of systems thinking about design, but it also has an overt policy overlay with some of your colleagues at the Bush School. Because all the things I talked about in the early part of the talk very much have a policy overlay of what are the implications of the science, technology, engineering we're doing. So we've actually created this 7th thing uniquely and specifically with Texas A&M to foster that opportunity. All right, so I'm almost done. So, if you want to talk about any of the things I've talked about, we have lots of time still to ask questions. Please do that. You get extra credit if you ask a question. There's also my email. I'm the only person who reads my email, and I actually do read it, so don't hesitate to ping me. But also, if you're interested in our student programs, our postdoc programs, the insect centers, those people would love to talk to you. Feel free to invite them to College Station as well. They'd be delighted to come. And if you don't happen to know Diane here, she's a bundle of energy. She lives to sort of make Los Alamos connections. She talks to us almost every day. Diane is a great resource, as well as the National Labs office here, as ways of going forward. So to conclude, and I'll put the emails back up again, I've tried to give you a flavor of sort of what Los Alamos is in a facts and figures sense that was hopefully useful. Tried to give you a sense of what our mission is from the most sort of laser focused national security all the way through fundamental science. And the fact that on the one hand, it's all connected. And on the other hand, you can live as an individual anywhere across it. I think one of the strengths of most of our folks is they end up having multiple careers. You can get tired of the grind of being a single investigator and writing a proposal every year. You can go work on bigger programs. In many places, you have to go find a different entity to go work for. You can work for us your whole life and do 3 or 5 or 10 different things. And that's really one of our strengths. And then try to give you a flavor of how we're trying to partner and collaborate with all of you. So I will stop there. I'll let you scribble emails if you want, and I'd be happy to answer any questions or have any discussion with folks on hand. So questions?
Thanks, John. That was a great talk. Questions? We have the portable microphone.
Yeah, so you understood correctly, and I would say it's in particular in the space of weapons design, but I think it's more broadly than that. So anybody who's worked in a field for their entire life has has a deep understanding of the field and preconceived notions. That's what makes them leaders, but that can also cause you to have blinders. So at a level of detail that I can't talk about, there is a particular design approach that the United States takes to its nuclear weapons. Not all other countries that have nuclear weapons have that same design approach. So if you give a well-trained US designer, the partial blueprint, the partial design concept of somebody else's stuff, they'll say that doesn't look like our stuff, it can't work. But young, smart people aren't as wise, but aren't also as stuck in their ways as our senior people. They just go at it and say, well, let's see what we can do with it. And there are a number of cases where they've concluded differently than our most senior people, because the counterpoint to wisdom is preconceived notions. So my example was the weapons program, but I think it applies across a variety of fields. No, so you would hope that you would hope that the most senior faculty have a higher probability of breakouts than the newest undergrad you just came to Texas A&M last week. The truth is, there's some that interaction is the most important thing.
So there's a question from in chat by Nick Sansev. How affordable is it to live in the area?
So good question. So I would say it's kind of in the eye of the beholder. So I'm somebody who grew up in the suburbs of Los Angeles. I would say Los Alamos is pretty affordable by comparison to that. If you come from the Bay Area in California, it's very affordable. If you come from College Station, it's probably fairly expensive. So I think the challenge at the moment is actually not so much the price point, but we do have an availability problem. So some of my slides showed pictures of Los Alamos. We live on the top of a mountain at 7,500 feet on finger-top mesas. It's decidedly beautiful, but if you're on mesas, there's only so much place to build. We have a bit of a housing crunch at the moment. But in most cases, especially for students or postdocs who come for a short time, as long as you plan ahead, you can find a good solution. But if you just drive in over the weekend having nothing, thinking you're going to find an Airbnb that'll take care of you for the summer, you're going to be sadly disappointed. You had this one here.
Oh,
question was.
I have a question.
So let's do one in the room here, and then we'll do one on Zoom next.
Hold on. Just a second.
Sorry. As far as for where exactly all the scientists are they primarily in New Mexico, or is there a lot of different locations throughout the country which through which they're employed?
Yeah, so I would say, before 18 months ago, it was 99.9% in Los Alamos, because we don't, so as I mentioned early in the talk, Sandia National Laboratories actually has 2 campuses. We just have the one main New Mexico campus. And other than a small handful of people who are at the IAEA in Vienna or an assignment in DC, everyone was in Los Alamos. One of the things we're trying to figure out at the moment is how can we take advantage. I mean, if there's a silver lining in all this pandemic stuff, we've learned better how we can all work from home, work remotely, do Zoom, whatever. We're trying to strike the balance of the vast majority of people need to be at the lab because collaboration and teaming is so important. And for a lot of our nuclear stuff and our security stuff, I hope we're not discussing classified information on Zoom. That's a different kind of problem. But at the 5 to 10% level, we can have really smart people contributing to important problems further away because we figured out technology. So we're moving from everybody in Los Alamos to now almost everybody in Los Alamos.
Valerie, you want to ask your question?
Yeah, I have a question. In the first generation of Los Alamos lab, there were giant figures such as, to say, Fermi, Bethe, and Feynman. Everybody knows these names. Do you have comparable scientists now in your lab?
So present company excluded, of course. So I think, so it was a special time during the war. If you look back and people, it was almost in the Manhattan Project, something like 15 of them went on to win the Nobel Prize. I think it's probably arrogant to say I have 15 future Nobel Prize winners in the lab today. But yes, I'll give you one example. There's a woman named Betty Korber who contributed early in bioinformatics to the setup of databases. She's the one who designed the HIV mosaic tests, HIV mosaic vaccine that are currently in clinical trials today. And she's also the first person who found the first change in variant of COVID when it went from this initial strain that was sort of came out of China to came out of Germany. I think Betty is of the caliber of the kind of people around in that project. And I think history will tell, in 30 years, whether 15 of us will win the Nobel Prize in the next 20 or 30 years. I think the other part of your point that's important, though, is it is true that we're so focused on teaming and collaboration, we have less singular people like that. So that I would say that's a feature. I mean, we have people just as smart, but because they're working in teams, they don't get recognized in the same way that, say, physics in the 50s did.
Mm-hmm. Thank you.
We have one more question in chat, but let's first.
Yes, so I think it was kind of alluded to with the nuclear posture review coming out, but do you see, especially I guess as it relates to sort of the more nuclear weapons work, a big change in focus between like administrations, or I guess, really any change in focus across different like political parties and agendas?
Yeah, so good question. I guess I would say there's actually less change than you might guess. I mean, so let's just take the independent of one's personal politics. If you take Obama's view, which was fairly, nuclear weapons make them irrelevant, Trump pretty proactive, Biden similar but different to Obama. At the speech level, they sound different. If you look at their respective NPRs, they look pretty similar. And so I think, the notion that it would be great to have a world where you don't have nuclear weapons, that would be a really good place to be. But it's also a bit naive to say they're just going to go away. So if they're going to exist, we probably need to lead in that space and make sure that's pretty independent of administration. I think the thing that has actually changed more, and again, this is not a political statement, it's sort of a landscape statement. There was a period where the Soviet Union was the well-defined single adversary. There was a long period of sort of multi-country terrorist stuff. Nuclear weapons aren't so useful in sort of 9/11 kinds of scenarios. The emergence in particular of China and now Russia, you've now got to think about, you have two near peers. How do you think about that? I think that's the biggest question that's being thought about. That's not a Obama, Vice Trump, Vice Biden thing. It's how do you think about that space, especially in the case of China, where they are a very vibrant, scientifically centric country. There is lots we could and should do with them. And they have political beliefs as a government that don't quite align with ours. That's the new question, which the NPR is thinking about pretty hard. But that's not a political thing. Or that's not a US political thing. That's a broader geopolitical question.
Want to unmute and ask a question?
Dave, can you ask your question now?
So I would say in general, yes. I don't think I know the specific program that the question refers to, but for example, there were the set of centers that I showed you. A number of those centers have what are basically faculty sabbatical-like things. So they'll bring a handful of faculty to come spend the summer with us. And the best thing about bringing faculty is they bring their students with them. So there are programs like that. There are programs funded by NNSA, like the Centaur program here, that people can be here and have partnerships with us. And there are a variety of other things funded by other agencies. So I think there are similar things like that. And frankly, that's a place where Texas A&M and the University of California have an unfair advantage because they're part of the actual management of the laboratory. And so when we think about partnerships, we think about the universities geographically closest to us in New Mexico. We think about our two parents, University of California and Texas A&M. And it's good that UC and Texas A&M have sort of different perspectives, different strengths, because that makes us better. And then we think about everybody else.
Right, there seems, Chang, you can ask.
Hello. I have one question. So at the beginning of this talk, you mentioned that one does not have to be a citizen to work for Los Alamos. But do you put any kind of restriction on those foreigners? Like what kind of research they can do or they cannot do?
Right, so I guess I would say not restrictions, but to be straightforward, probably reduced opportunity space. So is the core of the nuclear weapons program classified? Yes. Can we let someone who's not a US citizen see the design blueprints of a nuclear weapon? That would be inconsistent with our security posture. So there are some opportunities that aren't open to you if you happen not to be a US citizen. But as I hopefully tried to convey, there's lots of opportunity across the whole space, large parts of which are open to everybody. And so when we get it right, our open, fundamental, basic research is open to the smartest people on the planet, and Americans don't have a premium on that. But our very most protected national security stuff is US only. So I think it's more of a reduced opportunity than a restriction per se.
Thank you.
Yeah, so the question is, are summer opportunities limited to physicists and postdocs? Will undergraduate nuclears have similar opportunities? Yes, absolutely. So I mean, given that I happen to be a physicist and this is the physics colloquium, I biased my remarks to physicists. In the spirit of full disclosure, I will say 3 weeks ago, I was at UC Berkeley's nuclear engineering department, which is almost as good as Texas A&M's nuclear engineering department, and gave the same spin on nuclear engine opportunities. And so I think one of the challenges is if you just say, we've got 2,000 students, come join us, that, at least my own perception, and I would welcome the feedback, that's not specific enough to say, what can I do? So I tried to be overtly specific in this discussion on opportunities for physicists. But yes, there are tons of opportunities for nuclear engineers. And the plot that I showed that had little stars where physicists live, I have a similar plot for nuclear engineers. And with apologies to my physics friends, there actually are more nuclear engineering opportunities across the whole laboratory. So yes, tons of opportunities for nuclear engineers at the undergraduate and all other levels as well.
I've always been interested in academics and this kind of research opportunities, but because of military obligations, it's not something I can really do over the summer or directly after college. Do you have like I'm wondering like some sort of pipeline or acquisition or working relationship with like naval nuclear propulsion or naval reactors? And if you have any faculty in that background, sir, what can you say about that?
Yeah, so several things. So one, there is a program, and I forget the acronym, I think it's Sarrao, where the one counterexample to your point is some of the students who are at the academies actually do summer tours of duty. There's a program for some of them to come to Los Alamos for the summer, but that's a small part of the overall military population for sure. But broader, yes, absolutely. So we have a very large veterans population. One, because there's a shared interest in national security. And frankly, when you complete your service, you've probably got a security clearance that, for anybody else takes 6 months or 12 months to get, you've got one walking in the door. So big opportunities in that space. And as you say, a big part of how we do our work being as important as what we do is a principle that the nuclear Navy has a different phrase for, but totally understands the same thing. So the disciplined operations that the nuclear Navy is exceptional at goes hand in hand with what we do. And there are tons of nuclear Navy alumni who are working for us for exactly those reasons. So there's a very sort of veteran and military friendly population problem.
Can you talk about some of the efforts and the interest of Los Alamos in the national quantum?
Yes. So let's see, I guess I won't go back. So I would say for quite some time, Los Alamos has had a strength in quantum. To the question about who are our future Nobel Prize winners, in the space of quantum, I would say Wojciech Zurek is somebody who's competitive in that space. So we've always had a strength in sort of the frontiers of foundations of quantum, including some of Feynman's famous talks we've given at Los Alamos. That's led to a strength in algorithms. So I think we're strong in quantum simulation and quantum algorithms. Probably 20 years ago, in the last sort of quantum renaissance, we dabbled in, can we be the leader in any particular device technology? Do you pick Josephson junctions? Do you pick ion traps? Do you pick whatever? We basically concluded, one, it's pretty expensive, and two, we weren't smart enough to pick any particular technology. So we're intentionally technology agnostic. So we've had a broad effort in quantum simulation, quantum materials, quantum sensing and communication, but not quantum devices. Over the last 3 to 5 years, there's been a resurgence of funding in quantum, as you know personally. So we're doing a lot of work in materials for the moment, sort of being underlying device stuff. There's an awful lot of work among our nuclear physicists and particle physicists doing foundational quantum stuff like Wojciech's work. And then just in the last year, all those pieces have come together in what's called the Quantum Science Center, which is a large scale initiative where we and Oak Ridge and Fermilab are all partners working together with some of our university colleagues. I think the next frontier is probably quantum sensing, quantum networking. So we've had a long history in quantum key distribution, quantum communication. We actually have quantum technologies deployed on the grid in Tennessee for cybersecurity. So we're trying to take that to the next level, including foundational work to that. So hopefully that helps. Yep. Good. Yes.
So are the statisticians limited to only working on the data science projects, or can they work with scientists on all sorts of things?
No, so good question. So yes, there definitely is a home for statisticians. I would say we are, and I think my statistician colleagues would agree, we're less strong in the fundamentals of mathematics than we might like to be. We are quite active in applied statistics, not just in data science, but if you go back to the weapons program stuff, one of the questions becomes, lots of policymakers want to answer the question, is it going to work or not? Yes or no, no excuses. That's not a very disciplined statistical approach. So one of the areas we've been very active in is questions of uncertainty quantification. And can you say with the following probability it will work or not work? That informing policymakers is huge. There's a framework called margins and uncertainties that says, if you know the following things well enough, that gives you confidence the final thing will work. Articulated poorly by me, that's what statisticians live for. So active in that space, also active in all the public health stuff. Because again, the notion of, are you going to get COVID tomorrow or not is an unanswerable question. But how you do the epidemiological modeling in a forecasting way is intrinsically a statistical. The group leader of our theoretical biology and epidemiology group is in fact a trained statistician for exactly that reason. There's another chat. Okay. What would an ideal student intern be in terms of technical knowledge and skill set? So I guess I've hopefully painted a picture. There's not any particularly preferred technical discipline. I think the attribute that's most important is somebody who is interested in interdisciplinary work and interested in being flexible. So, if you want to do just one thing and do it really well all by yourself, then being an academic professor is a pretty good path. There are lots of really great collaborative professors, but there are some professors who work very much by themselves. That's really not part of our culture. So we are very much a teaming, collaborative, flexible thing. So if you have those personality attributes, it's awesome. So I'd say for myself, my PhD advisor at UCLA had a mean time to degree in physics of 11 years. That was kind of scary and crazy. I came to Los Alamos. I think I'm flexible and relatively independent. I had more problems than I know what to work on, and I got a PhD in 3.5 years. And so for me, that kind of worked. If where you are, you need lots of structure and lots of direction, Los Alamos can be a tough place because there's sort of a fire hose of opportunity. So I think it's more personality features and sort of personal preference than any technical discipline. Because I think one of the strengths of us is it's hard to think of any technical discipline we don't have somebody who's among the world leaders in that space.
There are no more questions. Let's thank Dr. Sarrao again for a great talk.
Thank you all for coming out, and don't be shy about following up. We'd love to hear you and talk about other opportunities.